In the previous video, we took a look at the drawbacks to spanning tree, things that make spanning tree difficult to work with, some of the disadvantages of spanning tree. That wasn't to put spanning tree down, but just to get some background on what makes spanning tree difficult to work with from a service provider's point of view. And that video kind of culminated that whole introduction chapter, that whole background of spanning tree. So this whole video series was really, I imagine just creating this video where we're starting now. But then I thought, well, it might be good to kind of give a whole background of spanning tree, and that kind of snowballed into this really long-winded discussion about the history of spanning tree and on the versions of spanning tree and the spanning tree toolkit, et cetera, et cetera. And so we'll reference some of those things that we talked about earlier, but if you wanted to just skip all that, I think you'll have no problem following along starting here. So in this video, we'll take a in-depth look at how a service provider handles spanning tree, or how a service provider deals with spanning tree in layer 2 services. Um, in this video, we'll discuss how the service provider handles loop prevention within their own network and how they might have to interact with the customer's spanning tree instance. And then we'll take a look at Ethernet NIDs. If you're not familiar with them, we'll go over just quickly what they are, what they're used for, their capabilities, and then do they run spanning tree or not? How do they treat the customer's spanning tree BPDUs? And then we'll also look at using a switch as a NID. This is something that sometimes comes up where instead of using an actual Ethernet NID that's purpose created for Ethernet services, you might use like a Cisco switch as a NID, and what implications does that have? And then that will probably end this first part that we're talking about here. And then the second part, we'll look at layer 2 protocol propagation, so specifically propagating spanning tree BPDUs, but we'll just look at layer 2 protocol propagation in general. And then we'll look at storm control, and then site redundancy and loop prevention. So this is a really big topic. There's different ways to handle this. There's different methods, whether you're using VPLS or EVPN. So that's a really big topic in itself. And so for this first part, I have some diagrams here to talk about the different topologies and technologies that the service provider is using in their domain. And I've got these extra redundant links here. Like there's these 2 links to this one site, this 2 links to this other site too. So for the purpose of this video, you can just ignore these. We're not going to talk about site redundancy. It'll just make things a little bit too complicated. So we'll start off first with the case where the service provider itself is running spanning tree in their own network. So in this case, the service provider has a layer 2 access network. They're not running MPLS here. There's many different reasons why this might be the case. Sometimes it's the case that this is just cheaper. Some service providers might think this is actually more simple. They don't have to run OSPF or ISIS and LDP and RSVPT and BGP and stuff, and they can just kind of get some cheaper purpose-built devices just to do layer 2 forwarding. So service provider has a layer 2 access network, and in this case, they have a partial mesh. They don't have a perfect ring. So if they just had a single ring like this, they would probably use a ring redundancy protocol, but they don't. They have some extra links. And when this happens, you theoretically can do things like you can make multiple rings, and you can do like an open ring and stuff, but maybe they have many. Their network is too meshy to do something like that. So their only option now is really just to do spanning tree, to handle loop prevention in their own network, because they've got their own layer 2 access network here. So now the discussion becomes, how are they interacting with the customer, with the spanning tree between the service provider and the customer? Because the service provider has their own spanning tree instance, the customer has their own spanning tree instance. Well, the question is this an overlay or not? And the only overlay option here is really just Q&Q, because remember, this is not an IP network. They're not going to be using MPLS or VXLAN, etc. So really the only option to create an overlay here is Q&Q. So let's talk about the case where they're not doing Q&Q. It's just a single flat layer 2 domain, essentially. This is a case that's not seen very often because presumably the service provider has multiple customers that are attached to this metro area, to this metro layer 2 access network. If they don't do Q&Q, they have to dictate to customers that either you can't use VLANs, we're just going to put all your traffic into one VLAN and you can't tag VLANs, or you can use this range of VLANs. There might be cases where this is acceptable, where the customer, they have some relationship with the customer and they know that, oh, the customer is just attaching like routers to this layer 2 service and they're running their own routing protocol over this. They're not using VLANs, they're not doing trunking. Or they know that, okay, this customer only needs 10 VLANs, that sort of thing. So this case is very difficult because the service provider's layer 2 domain is blended, extended into the customer's layer 2 domain. So in this case, really you're going to be running spanning tree with the customer. And that's the case that we saw in one of the previous videos talking about the spanning tree toolkit, where Cisco had this diagram of a root card where they said, okay, you've got this service provider network, the spanning tree root is here, and you're going to put root guard on these ports because you don't want the customer to have the root, be able to change the root, change the spanning tree topology. And I said, yeah, that doesn't really happen. Well, yeah, this case is very, in my opinion, kind of contrived, where you've got this layer 2 access network, you're not running ring redundancy, you're not doing Q&Q and creating overlay. Okay, you've now stripped the problem down to, yeah, you're going to have to run spanning tree with the customer. And your only real protection option is just to do root guard, because as we talked about in the previous video, in this drawbacks of spanning tree, there's no way to say like this is spanning tree instance X and this is spanning tree instance Y. So, and I said that it's kind of a misnomer that you want that you can have different spanning tree instances or different layer 2 instances because they're all one and the same layer 2 domain. The layer 2 domain is really defined by the flooding domain. But now let's talk about, one thing before we move on. Another option is just to filter BPDUs. So the customer sends a BPDU and you just filter it. You just do a BPDU filter on all of these ports towards the customer. That would isolate this spanning tree domain. It does create the problem that now the customer sites cannot see each other at the spanning tree level. It doesn't look like they're connected from spanning tree's perspective. The BPDUs are not propagating to their sites. So that can be a problem. And if you need that to handle loop prevention, that creates a problem. And even though I said we'll ignore loop prevention for the moment, let's just talk about it very briefly. So let's imagine that these links are not there. So each site just has one access circuit into the service provider network. Well, there's nothing that prevents the customer from at any time just connecting another link between their two sites. And the service provider has no control over this. The customer can just do this at any time. And now they've created this loop here. Well, if you can propagate the customer's BPDUs, this loop will not form because the customer sends a BPDU here, it gets sent here, and depending on where the root is, this link is going to be blocked, and the now you don't have a loop, because to these switches, if this switch sends a BPDU and it comes in here, it really looks like these two switches are directly connected here. So if they make another backdoor link, spanning tree handles this loop. So now let's talk about Q&Q, really the only overlay method that you can do here. So with Q&Q, it's kind of interesting to consider that now you've actually broken the layer 2 domains, because where I was just saying it's a misnomer to try to make this layer 2 domain separate from this layer 2 domain because they're all one and the same flooding domain. Well, with an overlay, you actually do that because you encapsulate the customer's traffic with the S tag, the second .1Q tag, and that creates an overlay to where the service provider's layer 2 network is now an underlay. The customer's service is this overlay, like a service, and like this application now that's using the .1Q overlay. So because of this, you can have spanning tree instance isolation. But there's a catch to this, which is that you may need to do tunneling. So I'll explain that here with this Cisco document. This is a Nexus 9K document that talks about doing Q and Q. Okay, so this page says that the spanning tree protocol must run properly, and every VLAN should build a proper spanning tree that includes the local site and all remote sites across the service provider infrastructure. So what they're saying is that you should propagate BPDUs. Spanning tree BPDUs should be transported from site to site so that spanning tree can build a tree that includes all the remote sites. So they're saying that a BPDU is sent here, and it needs to be sent out to the other remote sites so that the other sites build a spanning tree where this service provider network just looks like a big layer 2 switch, a layer 2 hub essentially that's just forwarding the BPDUs and not participating in spanning tree. That's what makes this overlay concept so powerful, is that the service provider can transport the customer's layer 2 traffic without it impacting their underlay. So, but the problem is that a BPDU is received here, and let's say, okay, it's going to forward, this ingress switch is going to forward it out to the other customer sites. This multicast traffic is just going to flood it. Well, this switch receives it, and it sees a destination MAC address that's either the IEEE MAC address or the per VLAN spanning tree Cisco destination MAC address, and it has a entry in the forwarding table to process it to the CPU. And to actually demonstrate this, I'll pull up a switch here to show what I'm talking about. So to demonstrate this, I've just got a basic layer 2 switch, and you can see that there's certain MAC addresses that the forwarding entry is go to the CPU. So this is, I believe these two are the IEEE and per VLAN spanning tree destination MAC addresses, and it's going to consume those at the CPU. So the question is, how do you prevent that? How do you prevent these switches in the service provider network from processing those? Because you're creating the overlay with the .1Q tag, but the destination, the Ethernet header of source and des MAC is not changing. Well, the answer is that you have to do layer 2 tunneling. So you have to, as the BPDU is received here, you have to encapsulate it with another Ethernet header with a different destination MAC address. And if you just choose any multicast MAC address that is not being consumed by the CPU, then you'll bypass that, and all these switches will just forward as if it's just regular customer multicast traffic that they need to flood. And then these egress switches will also have to have this same layer 2 tunneling configured to remove that extra layer 2 and encapsulation. So that's what this document is talking about here with layer 2 protocol tunneling. It's just saying that you have to encapsulate the layer 2 protocol access with a special MAC address. And what's kind of interesting about this concept, to kind of step to the side and talk about this idea that you're allowing the customer sites to build the spanning tree topology that includes all the remote sites. You're propagating BPDUs. Well, there's sometimes two different schools of thought of this, is that on the one hand, you might say, yeah, you should allow all the remote sites to see each other at spanning tree level because this is a layer 2 service. On the other hand, you could say, well, you should not allow spanning tree instabilities on one site to affect another site, so you should actually isolate sites. And this idea kind of comes up with in data center discussions about doing a data center interconnect, a DCI, between two data centers where you want to stretch layer 2. Some data center technologies like OTV, they by default do not transmit BPDUs across the overlay. They do not propagate BPDUs from one data center to another. And the argument is that spanning tree isolation fundamentally limits the fate sharing between data center sites. An STP problem in the control plane of a given site will not produce any effect on the remote data centers. So you have these kind of two conflicting ideas. Should you propagate BPDUs to all the remote sites? Or should you just cut them off so that each site is a separate spanning tree instance? My opinion is that in a service provider context, the service provider is providing a layer 2 service that should be completely transparent, a transparent LAN service, it's sometimes called, sometimes abbreviated TLS. So with that in mind, the service provider should not be blocking any traffic. So the customer should have the opportunity to propagate BPDUs or not. The customer can configure BPDU filtering if they want to not have spanning tree running throughout their entire layer 2 service, throughout, including all their remote sites. They should have the opportunity to control that. Just like the service provider never blocks anything at layer 3 on a layer 3 service. The OTV case is a little bit different because this is one entity, one enterprise deploying a layer 2 stretch service for themselves, for their own data centers. So it's different than a service provider dictating to the customer that, yeah, we're not going to forward your spanning BPDUs because you should isolate spanning tree on your remote sites. I think that should be up to the customer to decide. Okay, so we're talking about Q and Q. You would need to encapsulate BPDUs, have them propagate to all sites. But now the spanning tree has their own spanning tree instance. So the service provider can run spanning tree on the SVLAN instance. And this is a completely separate spanning tree instance than the customers, because the customers' BPDUs are just getting tunneled throughout the service provider's layer 2 access network. So yeah, I believe that's really all there is to talk about there with the service provider running spanning tree. We didn't really go over kind of this about just the operation of Q and Q. If you're not familiar with Q and Q, it allows the customer to send any tag traffic. So this says some C tag here. And at the switch, the S tag is pushed on top. So it's a second tag that's pushed on top of the customer tag. And this is what creates the overlay. This is what allows every customer to use 4094 VLANs. And you can have up to 4094 customers connected to this layer 2 metro network. Perhaps you would have some VLANs used for management of the service provider's network. So, maybe you can have around 4,000 customers, which is probably plenty. So let's move on to the next case, which is an access ring. In this case, the service provider is still doing layer 2 forwarding, but they're not running a spanning tree instance. They could, and if they are running spanning tree here, then it's just the previous case that we talked about. If they're not, then they're using some ring redundancy protocol here, such as G8032. So in this case, it's kind of the same thing as we just talked about, where either the service provider is doing Q and Q or not, overlay or not. If there's no Q and Q, you have the same problems where, can you propagate the customer's BPDU from site to site? If you can, then you can allow the customer's spanning tree to work, and the service provider doesn't have a spanning tree instance. Their loop prevention is something different. You would likely need to tunnel these BPDUs because you'd have that same problem again, where the switch is likely already pre-programmed to inspect the destination MAC and punt these traffic with this destination MAC to the CPU and not forward it. So more likely you're going to be doing Q and Q though, and then you still have the same issues, to tunnel the BPDU so that the switches here in the middle don't process the customer's BPDUs. So yeah, there's really nothing too different here with when the service provider is running a ring redundancy protocol. It's just that now they don't have their own spanning tree instance. So there's no way to have interaction with the service provider spanning tree instance and the customers. So now let's talk about when you have layer 3 access. So in this case, I've colored the links as blue to just denote that these are not layer 2 links, these are now layer 3 links. They have an IP address, and you're doing IP MPLS here. So now the underlay is layer 3 routed, so it's inherently loop-free. That's the loop prevention mechanism of the service provider's underlay here. The overlay loop prevention is something different. So where when we were talking about Q and Q before, the overlay loop prevention was still either spanning tree operating on the S tag or the ring redundancy protection. In this case, the overlay protection is going to be something else. So with VPLS, the overlay loop prevention is split horizon based on the pseudowires all belonging to the same split horizon group. So we can just do a kind of a brief overview of how the pseudowires work in VPLS. With VPLS, every PE has a pseudowire to every other PE participating in the same VPLS domain. So, let's say these are the PEs here for this layer 2 service. So each PE is going to have 3 pseudowires, one to every other PE. There's a full mesh of pseudowires here. So any bump frame that's received on one PE is going to be flooded out all 3 of the pseudowires. And as that bump frame is received on the pseudowire of other PEs, they denote the source MAC address. So they do MAC learning on these pseudowires as if they were a pseudo port. And then they learn, okay, this source MAC address is reachable out this pseudowire. But also these pseudowires are all in the split horizon group, which means that any frame received on one pseudowire cannot be flooded out other pseudowires. Because of this full mesh, you can use the split horizon rule, and that's the loop prevention for VPLS. And these pseudowires are configured either manually, where you literally go onto every router and say, this is pseudowire number 1 to this PE, to this PE, to this PE. And then you use targeted LDP to bring up the session for the pseudowires and exchange the service label for the pseudowires. Or more likely, you're going to do BGP auto discovery. You can do auto discovery of all PEs participating in the VPLS domain and then automatically build targeted LDP sessions to all those PEs. Or the last case, which is probably the more often used, is you don't use targeted LDP at all, and you just use BGP for auto discovery and signaling of the service label. You still functionally have all these pseudowires, this full mesh of pseudowires. It's just that you don't have the state of targeted LDP keeping all these pseudowires up to exchange the service label for the pseudowire. So VPLS, EVPN, is quite similar to VPLS. It's essentially a split horizon rule, but there's not pseudowires in the same sense where there's this state created. Instead, in EVPN, a PE advertises 2 routes for MAC address forwarding. One is a unicast lookup label, and one has the bum label. So the bum label just means forward this out all of your access circuits. The PEs don't have pseudowires that are learning MAC addresses because in EVPN, the MAC address learning is handled in the control plane. But it's still a similar, and ends up functionally being something similar where a bum frame is received. It's the ingress PE looks up its a flood list that includes all of the egress PEs and their bum label that they advertise in the EVPN route, and it floods it to all of those PEs. The PEs see a bum label, and they flooded out their access ports. So that's how loop prevention works with EVPN. And the bum label is also used to handle multi-homing, where the non-DF is not going to flood traffic onto the ES because it can, based on the fact that it's receiving this bum label. We'll of course look at multi-homing more in the next part. But that explains loop prevention within the customer's underlay and overlay. And then you still have the same considerations when it comes to propagating BPDUs between the sites. But now it's a little bit easier because you don't have to do layer 2 protocol tunneling most of the time, because the spanning tree BPDU is received here. The ingress PE is going to flood it out. Let's say it's VPLS, all of its pseudowires. It's going to encapsulate that frame in MPLS and forward it through MPLS. So these routers are forwarding based on MPLS. They're not looking at the destination MAC address of the customer's traffic, and so you don't have that concern where this switch here in the middle is going to process that spanning tree BPDU. So for that reason, you typically do not need layer 2 protocol tunneling, but you do have to pay attention to whether you're going to propagate the BPDUs or not. We'll talk about that more in the layer 2 protocol propagation section. And you still have the same issues about, well, if this customer connects a backdoor link, if you propagate BPDUs, you can handle that, etc. So for most service provider networks, they are going to be like this, where you're using IP/MPLS. And so you never really have that concern about how is my spanning tree going to interact with the customer spanning tree? Because the service provider isn't using spanning tree in their network at all. Even if they have a layer 2 access network, it's most likely going to be a ring, because a ring is the most economically feasible way to provide redundancy in some metro area. It's, you've got exactly one link of redundancy and no more than that. So it's quite uncommon for a service provider to run spanning tree in their own network and have to worry about it interacting with the customer network, because even if the service provider is running spanning tree in their layer 2 access network, most likely they're going to do Q and Q, and therefore their spanning tree instance is separate from the customers because they've created that overlay and underlay through Q and Q. Okay, now let's talk about Ethernet NIDs and how they affect spanning tree. So I've got this image here of like just kind of a generic Ethernet NID. So if you're not from the US, you might have another term for this. In the US, we use this term NID, which stands for Network Interface Device. And this is really just the service provider's handoff device. It allows the service provider to create a clear demarcation point for the service. So I've got, I added to the diagram these devices here where these are like the NIDs. So you might ask, well, why do we need this? If the customer's device supports SFPs, can't we just take this fiber and just plug it directly into the customer's device? The answer is, yeah, you can do that, and the service will work. But there's many problems with this, because what happens when you have to troubleshoot this circuit? If the customer says, hey, I'm getting some packet loss, I'm seeing some problems with the circuit, how does the service provider test their end? Because we're assuming that the service provider owns the fiber until it gets into the customer's premises, into the customer's building. So that's the purpose of these NIDs, is that the service provider owns this NID, and the service provider can test from here to test that fiber path that they own. And we'll talk more about kind of intrusive testing that these NIDs can do in a second. But another purpose of these NIDs is to do multiplexing, because the service provider might be offering multiple services: an internet service, a layer 2 VPN service, a point-to-point layer 2 service, a layer 3 VPN service, voice service, etc. And they can multiplex these all into like a single 10 gig fiber. And just as a side note, you would typically never oversubscribe this circuit going into a customer's premises, going to the NID for this customer, because you don't want to do something like a 1 gig circuit here and have like multiple 3 or 4 500 meg services that you're offering, because this customer could easily just max out all of those at the same time and they'll get upset that, hey, why are I can't use all my bandwidth on all these 4 services. You're guaranteeing me 500 megs on all these services. Now, if we talk about oversubscription for an entire metro area, yes, of course, you're going to oversubscribe that. Of course, if you have hundreds of residential customers, you're not going to have some kind of 400 gig uplink for that metro area so that all customers can use a full 1 gig at the same time. No, that's of course completely unreasonable. So it's really the only choice is to oversubscribe there. But when it comes to one customer's service, this one NID, yeah, you're not going to oversubscribe that. I just wanted to mention that as a side note. So some other things that these NIDs do are, used for troubleshooting, as we stated, monitoring. The service provider is probably going to monitor these within using SNMP. And although these NIDs forward traffic at layer 2, they're quite different from layer 2 switches, because they have specific features that are added to them for use for Ethernet services. So one of them is these OAM tools. So OAM, if you're not familiar with that, stands for Operations Administration Monitoring. And this is just kind of a blanket term for the suite of protocols that allow for, monitoring and troubleshooting, et cetera, for a particular technology, in this case, Ethernet. So these will be called Ethernet OAM tools. One is CFM, which is Continuity Fault Management. And what this is basically a way to do things like ping at layer 2, like an Ethernet ping, which is called a loopback message. And you can do a Ethernet trace route, which is called a CFM link trace. So it brings these kind of troubleshooting tools to Ethernet. And then another thing is that you can do a continuity check, where this is maybe more often seen on layer 2 point-to-point services, where maybe you've got a point-to-point service from site 1 to site 4, and you'll run CFM here and here. And you can define a rate that this is running. It can be in the milliseconds, maybe maybe every 10 seconds. There's a layer 2 probe that goes from here to here. And then you can graph that out and, do kind of service monitoring and assurance that, yeah, this service has been up in the last month there's been no outages, that sort of thing. And then we've also got Y1731, which is performance monitoring. It uses CFM, and it runs these types of like SLA probes to measure delay and loss, but at layer 2. And what Y1731 does is it uses CFM, but defines the CFM frame formats that are used to do these delay and loss probes. And then something different is the RFC 2544 test. So this is a test that is quite old. This RFC is from like 1999. And this RFC defines a way to benchmark a network device in the lab. And this test has kind of been hijacked to be used as an Ethernet service activation test to validate speeds for a layer 2 service. But what this test was really meant for was for vendors to have a standardized way to be able to advertise that, yeah, this device can do whatever it is, 200,000 packets per second at a 64-byte frame size, that sort of thing, and with latency less than half a millisecond, etc. That's what this RFC was for, but it's been used now to do Ethernet service activation tests and validation and troubleshooting. You may have, if you're a customer of a service provider, you may have had this happen to you where you submit a ticket saying, hey, we're having some issues with this circuit. And the service provider says, okay, well, can we intrusively test this? We're going to take down your service. Well, what they're most likely doing is running a test like this RFC 2544 test, where they, let's say you have a 500 meg circuit between these two sites. They'll shut down the access ports, the customer-facing ports, and then they'll run an RFC test at a 500 meg throughput rate. So like this side will send, and this side will measure, and we'll receive, and it will report if it received the full 500 megabits per second of traffic. And this test steps through different frame sizes one by one. So usually there might be like 6 or 7 frame sizes that you test. You can control this, and it will be like 64 bytes, 128 bytes, 256, 512, etc. You'll do 1518, and maybe you'll do one jumbo frame. So this test isn't quite a real world test because it steps through the frame sizes one by one. 64 bytes for a few minutes, 128 bytes for a few minutes, and I believe when it does the latency detection, it only does that at the very beginning. Like let's do latency detection. Okay, now let's do the throughput of 500 megabits for 64 byte frames. So the newer Ethernet service validation test these days is Y1564. And this has a lot of benefits. It can also test a jitter. You can do multiple flows at once. It mixes rates. It doesn't just do 64 bytes at one time, 120 bytes at one time, etc. And it can also do validate the QoS policies. So validate CIR and EIR that, the excess rate is getting marked down, things like that. So, and I also believe that this is much quicker to run. I think with the RFC test, you have to run it for a much longer period of time to get the same accuracy, the same level of assurance and validation that you can achieve with 1564 in a much shorter period of time. And also, as a side note, I think it's interesting to mention that with the RFC 2544 test, it's quite common to see some loss with a 64-byte frame size because if you've got very high rates, maybe you're doing like a 5 gig service on a 10 gig link. Um, some devices along that path might have trouble forwarding 5 gigabits per second of 64-byte size frames. So sometimes it can kind of cause this point of pain where you have to tell the customer, yeah, here's the results, and say, why is there 3% loss at 64 bytes? And be like, well, are you sending 5 gigs per second of 64 byte frames? Because at the 256 byte size, there is no loss. So the problem is that at such a high throughput, you need so many frames at 64 bytes. So it can kind of cause those issues. Okay, so some other things about the NIDs is that they usually have many less ports because a switch has the purpose of being used like in an office building to connect 24 to 48, PCs and printers, access points, etc. But the Ethernet NID has a much different purpose. Its purpose is to just hand off maybe a few services um, and to run these kind of Ethernet OEM tools, and it also does Q&Q. It has more fine-grained traffic conditioning support for policing and shaping, which is very important because it's quite often that a service provider provides a service rate that is lower than the line rate. So you have 500 meg service on a gig line, 5 gig service on 10 gig port, etc. So service provider has to traffic condition so that the customer can achieve their 5 gigs, but also cannot achieve higher than that. Another function that these NIDs can usually do is Ethernet loopback for testing. So you can send traffic here, and this NID can be configured for loopback. So it just loops back everything. Can be something useful for testing that this is something that switches can't do. So now let's talk about spanning tree. Well, these NIDs typically do not run spanning tree. Maybe they have the ability to run spanning tree, but it's probably going to be off by default. Because again, these NIDs are not switches. They're not meant to be used in like an office building and connected in a redundant fashion. These NIDs are just meant to hand off a service. Just one fiber uplink, most likely. Maybe in the redundancy case, we can talk about that later if you have two uplinks to two different PEs or two path diverse circuits, etc. And then one or more customer handoff ports. So how do they treat the customer's BPD if the customer sends a BPD in here? Well, by default, what I've always seen is that these NIDs are fully transparent LAN devices, that they'll just pass everything. They're not going to, you don't want them to process BPDs as if it's for them and they should participate in spanning tree, or as if they should participate in CDP or LLDP or LACP, etc. It just passes everything through. That's the default behavior that I've seen on most of these Ethernet NIDs. So they sometimes can run spanning tree if you want them to. But as a side note, I think it's useful to talk about the fact that when these NIDs run spanning tree, most likely they're not running Cisco's per VLAN spanning tree. That's a Cisco proprietary thing. They're also not going to run rapid per VLAN spanning tree. They could run rapid spanning tree, but the downside of that is, of course, you've got only one instance available for all VLANs. So most likely what I've seen is that multiple spanning tree is used on these things like these Ethernet NIDs. Maybe if we talk back with the layer 2 access scenario, these switches are most likely not Cisco switches. I mean, maybe back in the day they were Cisco ME series switches. These days, more likely you would see Sienna switches, things of that nature. And what I've seen is that they usually just support multiple spanning tree, because in that case you're using rapid spanning tree and you can do map multiple VLANs to an instance. It's kind of the best alternative to running per VLAN spanning tree in the Cisco world. So yeah, these NIDs really just treat spanning tree BPDUs as multicast and just forward it on. So now let's talk about using a switch as a NID. Well, this comes up sometimes because you may see this with kind of smaller service providers where the switches are cheaper. Well, I don't know if I should say much cheaper, because sometimes the Ethernet NIDs can be quite cheap. You can see them on eBay for like $200. But these switches might also be quite cheap. You might already have them around. And the one real great benefit is that the config is very well understood, that you can have people jump in to your service provider from like an enterprise background. And if you just throw these Ethernet NIDs at them, like this one here, this Adtran Ethernet NID, they're going to be very confused with how to configure that because it's completely different from a Cisco switch. You don't configure like I'd say, okay, we're going to do VLANs 100, 200, and 300 for data, voice, and IPTV. Okay, so make port 2 VLAN 10 or 100, make port 3 VLAN 200, make port 4 VLAN 300, etc. And then you go and, okay, I'm going to make this a trunk link. I'm going to do switch port mode trunk. I'm going to make this switch port mode access and VLAN 100. Well, no, that's not how these Ethernet NIDs are configured. Usually it's configured through the concept of like tagged and untagged VLANs. So it requires this a little bit of a mental shift to configure these because they are not configured the same as a Cisco switch. So the benefit of a Cisco using like a switch as a NID is that the config is very well understood by people that come from like enterprise backgrounds. Maybe you also need more port density for some reason. Maybe you're putting this in a multi-tenant building where you're gonna have many, many handoff ports. I mean, they do make Ethernet NIDs that have more port density. Of course, they cost more money. But that could be a reason you've already got this 24 port switch sitting there. Let's just use it. And often you're doing this when you don't need to offer like a business MEF style service where you don't need the OAM tools, you don't need Q&Q, etc. So as a side note, usually when you're using these Ethernet NIDs, this NID is a place where the S tag is pushed. So the customer sends a C tag here, and then this NID pushes the S tag, and then this PE receives the traffic with an S tag and a C tag already on top. That's usually the use case. That's usually the situation that I've seen. But of course, you can have the NID just pass through the C tag, and you can push the S tag here on the PE. Either way does work. So back to using a switch as a loop. Using a switch as a NID, you don't need all these tools. So you can use the switch in that case. So, but the problem with this is that you have to be very careful with how you handle spanning tree when using a switch as a NID, because as we talked about before, the switch can either process the BPDU, it's going to receive the frame, and look at the destination MAC, and that is punted to the CPU, or it can drop it. Usually these Cisco switches, like the 2960, is not going to have the capability to do layer 2 protocol tunneling like we saw in this document with the Nexus 9Ks, which are built for being able to do Q&Q. So it really limits you. It actually creates an issue because now you can't propagate BPDUs because the customer sends a BPDU. This is a Cisco switch now. Either the Cisco switch processes it in the CPU, or it just drops it. It just drops it here. You can't forward it on. So it creates the problem that now you can't allow the customer to see all of its remote sites from a spanning tree perspective. But in addition to that, there's some other considerations too with you have to be careful with not creating port type mismatches that can cause spanning tree to enter a blocking state. So I've got this document here that talks about troubleshooting spanning tree port VLAN ID and type inconsistencies. So in the previous videos, we talked about the spanning tree toolkit, and we covered these first three things. So just as a quick recap, there's multiple types of spanning tree inconsistencies that happen when you're using certain spanning tree features. So one is loop inconsistency. That's where you're using the loop guard feature, where the switch has loop guard enabled, and it stopped receiving BPUs on that port, so now it's not going to go to forwarding. It's implementing fail closed behavior instead of fail open behavior. The next is root inconsistency, where you've got root guard enabled on the port, and the port has received a superior BPD with a superior root bridge ID. That port enters the root inconsistent state. The other that we talked about was ether channel inconsistency, where you've got a port channel configured on the switch with port mode on. You're not using LACP. And the other side is misconfigured, and this local switch can tell that based on receiving BPDs with different source MAC addresses on multiple member ports of the same port channel. that port channel goes into ether channel inconsistency. Well, there's two others that we haven't mentioned before, which is one is port VLAN inconsistency, and this is where an untagged BPDU on a trunk has a different VLAN than the native VLAN. So I'll explain that a little bit more clearly because that's a little bit confusing when you first hear it. The next is type inconsistency, which is a little bit more easy to understand. Is where an access port receives a tagged BPDU, and that goes into type inconsistency. So in both of these cases, if the customer's port enters these inconsistency states, their service goes down. So this is something you have to be aware of when using a Cisco switch as a NID. So I think it's kind of interesting. If you want to skip this, you can, I guess, but it's interesting to consider what is this protecting from? Like, why does the Cisco switch have to enter these inconsistency states? Why are these configured and built into spanning tree within the Cisco switch? Well, the reason is that the Cisco switches can interoperate with IEEE spanning tree, which is just one spanning tree instance for all VLANs. That IEEE spanning tree BPDU has a different destination MAC than the per VLAN Cisco spanning tree BPDU. See, that has this MAC here, that has the C's here, ends in CCCD, and this is the IEEE spanning tree MAC. So Cisco switches can interoperate with the IEEE only switches because a Cisco switch sends multiple BPDUs on a trunk port. So it sends one IEEE BPDU for the just one in general, no matter how many VLANs are on that trunk. Then it sends one per VLAN spanning tree BPDU per VLAN on that trunk. Well, because of this capability of interoperating, because of this interoperability capability, you can enter these loop scenarios where this switch here is an IEEE only spanning tree switch. It only runs one spanning tree instance. These two switches, A and C, are Cisco per VLAN spanning tree. They operate one spanning tree instance per VLAN plus the IEEE spanning tree instance. Well, what can happen is that here we've got the root for VLAN 1, and this is the root for VLAN 2. This switch only is seeing the spanning tree instance for VLAN 1. So it says, okay, I'm forwarding here and here. Maybe this switch right here is actually blocking the port for VLAN 1. But for VLAN 2, this switch is the root. So for VLAN 2, what happens is that what can happen without this type inconsistency detection that Cisco has is that you can get a loop where all of these ports are forwarding for VLAN 2 because of this. Well, because this switch is sending the IEEE BPDU plus one per VLAN spanning tree BPDU per VLAN, this switch just treats the per VLAN spanning tree BPDUs as regular multicast traffic and forwards it on. This switch here then says, wait, I'm receiving a per VLAN spanning tree BPDU on an access port. And I failed to mention that access ports only send the IEEE BPDU. There's only one spanning tree instance here. They're not doing per VLAN spanning tree on an access port. So because it receives a per VLAN spanning tree BPDU on an access port, it goes into type inconsistency. So that's a very long explanation, but hopefully it gives you a sense of why this is the way it is to protect against these situations. So just to go a little bit more, to have a little bit more clarity of what the two types of inconsistencies are in this case. One is the type inconsistency, where a tagged per VLAN spanning tree BPDU is received on an access port. The other is native VLAN mismatch, where a BPDU is received on the native VLAN but has a different VLAN than the native VLAN this local switch has configured. And the way you can tell this is, I actually learned this pretty recently, is that the Cisco per VLAN spanning tree BPDU has this originating VLAN TLV added. So this says what VLAN the per VLAN spanning tree BPDU is for. So that's how the switches can tell. And you also might see in this case where you have two different native VLANs, if both these are Cisco switches and they're running CDP, you'll see CDP detect this because the native VLAN is communicated with in CDP. So you'll see CDP detects native VLAN mismatch, and you might also see spanning tree detect it through this mechanism. So this is all to explain that when you're using a Cisco switch as a NID, you have to be careful that you're not running into this situation, because this can happen if the Cisco switch is configured for, like, let's say you're using VLAN 100 for the customer for the service, and you say, okay, this is, but maybe you have a policy to do trunks on everything. You do, okay, switchport mode trunk, switchport trunk allowed VLAN 100, and switchport trunk native VLAN 100. Well, the other side could be doing switchport access VLAN 100 or something. And then they're going to get a mismatch because by default, because this switch is running spanning tree, and it's going to send a tag BPDU and the prevalent spanning tree BPDU, and that switch is going to receive and go, hey, why? This doesn't make sense. I'm going to block it. And the customer's like, hey, my service isn't working. This can also happen if there's some change in the config or something. You change it to a trunk with native VLAN, something like that. This can also happen when you're propagating BPUs just in general, just when you're not using a switch as a NID, you're not using any Cisco switches anywhere, but the customer can do this to themselves, because here, this switch here is a trunk and it's sending a per VLAN spanning tree BPDU, but all of these switches are access ports configured on the circuit for the VPLS service, and so if this switch sending a trunk, maybe this customer configures this switch as a trunk port there, and it brings in all their other switches. So this is just something to be aware of, that this feature is there, that this inconsistency can be detected here, how this works, so that you don't run into this. Okay, so what do you do then if you're using a Cisco switch as a NID? Well, in my opinion, I think the best thing to do is just disable spanning tree globally on the switch. And something that kind of sounds a little scary at first, like sometimes you hear people say, oh, you just never disable spanning tree. That's just a really bad thing to do. Don't disable spanning tree. Well, in this case, this switch is not used in a typical sense of like in an office building, etc. This switch is not going to be plugged into other switches. It's just being used as an Ethernet service delivery device. So in that case, just disable spanning tree. I mean, why not? The only problem is that you're not going to be able to propagate the BPDUs, but that's better than having to deal with these things like port inconsistencies and the native VLAN mismatch inconsistency, that sort of thing. Just disable spanning tree. The other thing you can do is just do BPDU filter inbound. Just configure on it, but you'd have to configure on all the access ports going to the customer. So if for some reason you want to leave spanning tree on, this might be in the case where you're using a switch as a NID, but then you've also got like a layer 2 access network. So perhaps you want to leave spanning tree on. But I would say just disable spanning tree globally. So I think that covers it for this video. I know it's been quite a long first part. And then in the next part, we'll go over layer 2 protocol propagation in more detail, storm control, how we can use that to help with in the event that a storm happens. And then we'll talk about site redundancy and loop prevention when a customer wants multiple layer 2 circuits into a single site.